So here's an outline of the talk. The basic topic of today's talk is something called energy conditions in quantum field theory. And so I want to start with a little bit of motivation and background. Just what are energy conditions? Why are they important? And then dive right into two recent results. So these are results for energy conditions that have been proven just within the last couple of years regarding quantum field theory. One of them is called the average null energy condition, which is abbreviated ANEC. And the second, which will be the focus of this talk, is something called the quantum null energy condition, abbreviated QNEC. And after sort of stating what these conditions actually are, what I'd like to do is dive into the proofs of these two statements and kind of explain what are the moving parts. So the goal is not to give sort of a nitty-gritty detail of the proof, but really an overview of the ideas that are involved and sort of to lay out the skeletal structure of these proofs, if you will. And I'm going to start with the average null energy condition and actually spend a decent amount of time on it because it turns out that if you understand the proof of the ANEC, you're almost like halfway there in terms of understanding the proof of the QNEC. And these two proofs are actually intimately related. The punchline actually is going to be that the main sort of the ingredient is causality. Both of these energy conditions follow from causality in quantum field theory. And I should mention that the ANEC proof, so the ANEC was proved by two groups independently in 2016 using very different methods. So one, the group of Faulkner et al. Used entanglement entropy methods, and the group of Tom Hartman et al. Used more CFT type methods and a light cone operator product expansion. And this is a theme that we'll see again and again in this talk, this interplay between ingredients from entanglement entropy, conformal field theory, and we'll even see ingredients that we'll use from algebraic quantum field theory. So stay tuned, and I'll try to point out these different ingredients as they appear. Okay, so energy conditions. What do I mean by energy condition? Well, we're just trying to answer this simple question, which is what constraints does the stress tensor TAMU obey in quantum field theory? Before we dive into quantum field theory, though, I think it's worth talking about another energy condition that's actually probably more familiar, and this is in the context of classical GR, which is the null energy condition, which I'll sometimes abbreviate as NEC. So in the context of classical GR, this is the null energy condition. It's the statement that the null-null component of T is greater than or equal to 0. And what do I mean by this? Well, by null-null component, I just mean that U alpha is some null vector, and I'm contracting that vector with T mu. So this component is restricted to be positive. Now, the way that this works in GR is that this is often taken as a reasonable assumption about classical matter, and then you ask what are the consequences of this within GR. And it's a reasonable assumption to make. For example, in the case of a perfect fluid, all you're asking is that the pressure plus the density be non-negative. But it has sweeping consequences in GR. So singularity theorems, area theorems, result on topological censorship, even holographic C theorems. These are all results that come out of this assumption about matter. So energy conditions play an extremely important role in our understanding of GR. And so, but this is GR, and so we can ask ourselves, okay, what about quantum field theory? Are there analogs of this sort of statement that hold in full quantum field theory? In particular, does the null energy condition itself hold in quantum field theory? And the answer is actually no. And this was known to QFT practitioners even in the 60s. So the null energy condition, the NEC, fails in QFT. And the idea is that this inequality does not hold. The energy density at a local point can actually become negative. And the quintessential example of this is just Casimir energy. So we're all familiar with sort of the Casimir plate setup. The idea is that for certain geometries and certain configurations, you can actually achieve a configuration where the energy density between the plates has points where it's actually negative. And for a more recent example, there are experiments with something called squeezed vacuum. Essentially what they do here is that they take pulses of lasers and shoot them at the vacuum, and they can achieve a configuration where there are pockets of both positive and negative energy density. So the point here is just that, net violation in QFT is not some weird artifact. It's really something you can actually see and construct in the lab. So the net is not true in QFT, and so this kind of brings us back to the question: well, what is true? What can we say about T mu and quantum field theory? Is there some lower bound, for example, that we can put here? We know it can't be 0, but maybe there's some other bound which tells you how low the stress tensor expectation value can go. And so you can ask this in very general context, but for the result that I'm going to discuss today is in quantum field theory in D greater than 2 space-time dimensions. What we're going to assume about this QFT is that it's unitary and Lorentz invariant, of course. We're also going to, for reasons I'll explain later, assume that it has an interacting UV fixed point. Great. So, 2 results. So these are 2 energy conditions that have been proven now within QFT within the last 2 years. So what are these 2 statements? The statement is that the following constraints are true in any D greater than 2 QFT with the assumptions that I've just mentioned. And the first of these results is the average null energy condition, or ANET. So what is this statement? So the statement here is that, okay, at a particular point, TUU is not greater than 0, but if I integrate it along an entire null line, then that quantity, or that average, must be greater than or equal to 0. And so I'm going to use this abbreviation a lot, this curly A, to abbreviate this integral. And the statement of the ANET is just that this operator A is greater than or equal to 0. So what does this mean, sort of physically? I kind of like this picture because what it's basically saying is that, hey, the energy density expectation value can dip below 0 at a particular point, but it has to be made up for on average. So if I do this integral, it has to be positive. And so even if I have a point where it's negative, it's surrounded by positivity. And so in that sense, the ANET is sort of a happy proof about a happy statement about quantum field theory. And just to make a connection, the ANET has important consequences as well. One that you might be familiar with is the Hoffman-Malazan conformal collider bounds. So these are bounds on 3-point function coefficients in CFT, and they follow from assuming the ANET. Great. So the second condition that's now been proven is the quantum null energy condition, or QNet. So with the ANET, we were doing an average over some null line. The QNet is making an attempt to come back to a local statement about T mu. So all of this is now happening at a particular point. And the statement is that this null component of T is bounded below by something which we're calling S double prime. And I'm going to define in the next few slides what S double prime exactly is, but for convenience, it's sort of nice to bring this S double prime to the left-hand side and define this as some operator Q. So I'm going to use this notation throughout the talk. And the constraint is that Q must be greater than or equal to 0. And just as a disclaimer, I'm sweeping under the rug factors of 2 pi and stuff like that. Okay, great. So what is this S double prime that we're talking about here? So again, all of this is happening at a particular point in space-time. So here's that point P. Now imagine that point P is lying on some Cauchy slice. That's given by this this big rectangle here. So the S appearing here is entanglement entropy. So how do I define entanglement entropy? Well, I need to take this Cauchy surface and I need an entangling cut. That's this red line here that passes through the point P and also divides this Cauchy surface into two regions, which I'm calling A and A bar. And when I do that, S is just the von Neumann entropy, the usual entanglement entropy of the region A. And just in case this formula is not familiar, or you're not familiar with the entanglement definitions, this is just a sort of a measure of the quantum entanglement between region A and region A bar. So that's what S is, but what is S double prime? So S double prime is a derivative of this quantity S as I deform the point P infinitesimally in the null direction. So just imagine that I'm taking this point P and just moving it ever so slightly infinitesimally in the null direction. Then S double prime is a measure of how much S is changing because of that. And let me be a little bit more specific about what I mean by that. So imagine that this entangling cut, this red line, has some intrinsic coordinates, y, and some space-time coordinates, x alpha of y. Then the entanglement entropy is a functional of those coordinates. And I can imagine taking a variation, a second variation of S with respect to those coordinates in the null direction. So U alpha is some null vector again. And if you do that, what you're going to find is that there's two terms. There's a term that's diagonal in y minus y prime, and then there's an off-diagonal piece as well. And S double prime is defined to be the coefficient of this diagonal piece. So that's the S double prime that's appearing as a lower bound of T U U. If this definition is too technical, don't worry too much about it. I think the physical thing to understand is that, if I move this point, of course the entanglement entropy is going to change, and S double prime is a derivative that measures that change.
You have a family of null. Why is the family? What's your family?
Y, yeah, right. Yeah, I mean, the Y is just let's say the coordinate along this red line, and you could have you could be deforming at different points. Okay, so what is this bound telling us actually? I think what's really fascinating and still actually mysterious about this bound is that it's bringing together two concepts that maybe we wouldn't expect to be related a priori. So we have energy on the one hand, and then we have entanglement entropy, or some notion of quantum information on the other. And I think that's what's really special about the QNIC is it's telling you that energy somehow knows about quantum information and vice versa. And this is something that is still, I think, to us very mysterious and worth really trying to understand. Okay, so that's the statement of the QNIC, but where did it actually come from? Yeah.
This is probably the obvious question. Is it obvious that if I just integrate over a null line, S double prime vanishes?
If you integrate along the null,
or it's positive, or like I'm trying to see if I now do the integral, if I reduce, if I derive the ANEC from the QNIC.
Yeah. So the short answer is that the QNIC implies the ANEC.
But okay.
He's asking, how do you see that?
Yeah.
You just put that integral over S double prime.
Yeah. So, so I believe this is going to follow from some positivity properties of entanglement entropy. So there's conditions of there are monotonicity properties of entanglement entropy. I think that's what's going to be linked here, but I have to remind myself on this. Great. So where did the QNIC actually come from originally? So the first paper that actually mentions the QNIC is a paper by Busso, Fisher, Leichenauer, and Wall in 2015. And what they were doing there was actually trying to say something about quantum gravity. And they proposed something called the quantum focusing conjecture, which is a statement about how, essentially how light rays should focus in quantum gravity. And what they noticed, though, is that if they took the sort of zero gravity limit of that conjecture, then they ended up exactly with the QNEC. And so they conjectured this quantum focusing conjecture, but then they also conjectured, hey, just for ordinary QFT, we expect the QNEC to hold as well. So subsequently, in a couple of different papers, this was actually checked in specific situations. So the QNEC was proven in free and supernormalizable bosonic field theories, and also in holographic theories. And so our result, in some sense, it kind of ties all these together and says that the QNEC is robust in QFT. Even more than just these specific examples, you actually have a generic proof within quantum field theory, and it's going to rely on causality. Okay, so what I'd like to do next is kind of dive into the proof of the ANAC and the QNEC, again focusing on sort of big picture ideas and the skeletal structure. But are there any other questions at the moment about just a statement?
Can you sketch a proof of classical energy condition? You just said, I think that it's an assumption.
Yeah. So this is now going to be different. So now we're actually going to start with causality and prove that these statements must be true. Typically in GR, you're taking the neck as an assumption. But it seems like a very reasonable assumption for a classical.
But then I think one who would expect that you should be able to prove it in a classical case with a certain type of variance. Classical.
Yeah, so you want to say, you want to take the QNEC or ANEC and then prove like,
yeah, it sounds
add in some limit.
surprising that you can prove one thing and then postulate another.
I mean, yeah, so what we're proving is not a positivity condition, right? It's some lower bound, which can be negative, right? So I think there's there is something fundamentally different about the quantum versions of these energy conditions versus the null energy condition, right? So yeah, I mean, these quantum statements are allowing energy density to be negative. It's just saying that, I mean, in one case, the QNEC is saying it can't be too negative, and in the ANAC case, it's saying on average, even if it's negative, somewhere it has to be positive on average. But they're still allowing for the fact that you can have a negative energy density. So, sort of kind of getting around what we know is not true. Okay, question. Any other questions? Okay, so let's dive right in. Okay, so the ANAC proof. I mentioned that there were two groups that independently proved the ANAC. For the purpose of this talk, I'm going to focus on the proof of Hartman, Kundu, and Tajdini. Just because I think at a conceptual level, sometimes it's easier to kind of go from this proof and understand how we prove the QNEC. Although, to be fair, we really did borrow ingredients from both proofs. Okay, so again, in the corner I've written this, oh sorry, it's cut off a little bit, but I've written the definition of this operator A. And what we're trying to prove is that A is greater than or equal to 0 as a result of causality. And there's going to be three main ingredients that go into this proof. One is, even before going into three ingredients, there's even more fundamental starting point, which is that we're going to be looking at this 4-point function. Psi is some scalar state, psi, psi. And I'm going to denote this 4-point function as little f. Starting with this 4-point function, we're now going to add three ingredients to understand this 4-point function. One is a light cone limit evaluation of this correlation function. Number two is causality. And number three is a boundedness property of this correlation function. And when we combine these ingredients together, that's how we're going to find that A is greater than or equal to 0. So what I'd like to do in the next few slides is kind of go through these ingredients one by one and say a few words about what's involved. So let's start with the light cone limit. So this is the limit where these two operators are coming into each other's light cones. So the picture to have in mind is here. The two operators O are coming into each other's light cone. Technically speaking, this is the limit where V is much less than 1 over U, much less than 1. And the main punchline here is that when you evaluate this correlation function in that limit, the operator A pops out. In particular, you're going to have f equal to 1 plus vu squared A plus dot dot dot. This is specific to 4 dimensions, but just to keep the formula clear. So the question is, why is it like this? Why does this operator A appear in this limit, in this expansion? And the idea is that the way we're going to evaluate this is to do the operator product expansion of O. So if you remember, the operator product expansion is just taking this product and expanding it in terms of just single local operators. So you have something like this. But we're working in a light cone limit, and it turns out that in that limit, the dominant contribution to this operator product expansion is the stress tensor and some particular derivatives of the stress tensor. And when you resum those contributions, you get exactly the operator A appearing. To say just a few more words about it, the light cone OPE is an expansion in twist, and the stress tensor and these U derivatives of the stress tensor are the minimum twist operators, and so they are the dominant contributions in this operator product expansion. And when you resum those contributions, you get this operator A.
I have a question.
Yeah.
So what happens to like twist 0 and twist 1, scalars and vectors? Why don't?
Yeah, so good. So in principle, you can have, spin 1 states won't appear because of just, there's an OOPE, if you don't have even spin. But scalars can in principle appear. It's going to turn out that, hold off on that thought. I'll tell you, there's a way you can essentially just project out scalars. So I'll say a bit more about that.
Is it the CFT or QFT?
Okay, good. Yeah. So so this is QFT, but the light cone limit is a limit that probes the UV of the QFT, and so the calculation is a CFT calculation. Exactly. But great question. Yeah. So we can get away with using CFT methods because the light cone OP is only probing the UV.
Did you say something about unitarity?
I have not yet said anything about unitarity. Yeah.
You're not in your list of assumptions.
Oh, sorry. The QFT is unitary. Yeah. Sorry, that was an assumption. It was written in small letters. But yeah. I was thinking unitary QFT. Great. Okay. So the punchline is really this expansion, and you knew something like this had to happen, of course, because we're looking at this correlation function. There's no A in this correlation function, so we have to do something to extract A from this. And the punchline is that if you look in the light cone limit, that's where A appears in this correlation. Okay. So now the next ingredient is causality. And what do I actually mean by causality? I just mean, ordinary microcausality, which is that operators at space-like separation should commute. And the punchline is that this assumption tells you something about the analytic properties of this correlation function. And just to kind of reiterate something probably everyone knows, but why does causality what does causality have to do with analytic properties of the correlation function? Well, you can kind of you can think about it in the following way, which is that imagine you're starting in Euclidean signature. Then everything's space-like separated, and your function is completely analytic. There's no worries about operators commuting. But now imagine trying to Wick rotate an operator into Lorentzian time. What's going to happen now is that operators are going to start coming possibly onto each other's light cones, and that's going to introduce branch cuts into your correlation function because now you have a choice of how you want to order those operators. So that's all I mean. All I mean is that in this way, causality is intimately related to the analytic properties or the singularity structure of a correlation function. And so you can ask this question of what is the domain on which a correlation function is analytic? And it turns out that just following through this reasoning, a simple way to state the analytic properties of this function is to make this following change of variables first. So let's let u equals 1 over sigma and b equals minus eta times sigma. Then as a function of sigma on the complex plane, this function is analytic on the lower half plane near the origin. That's the punchline that we're going to get from causality. Great. And the third ingredient we're going to need is some sort of boundedness property. And this really is pretty simple. It's just the fact that this function f can be thought of as an inner product. And as such, so this needs to be done with a little bit of care, but you can convince yourself that this is actually an inner product. And inner products are bounded by the Cauchy-Schwarz inequality. And so in terms of this function f of sigma, what it tells us is that the real part of f is less than or equal to 1 whenever sigma is real, and you're close to the origin. Great. So now we have these three sort of facts now about this function f. And the question is, how can we combine this to prove that a is greater than or equal to 0? And this is explained really nicely in a couple of papers where they sort of use this same machinery. But the basic idea is that is to do a kind of a smart contour integral. So you imagine the complex sigma plane, and imagine this this simple sort of half circle contour. Of course, we know that f of sigma is analytic around this contour, so this integral is really just 0. But there's two contributions. There's a contribution from the semicircular part, and there's a contribution from the horizontal part. The thing about it, what you'll find is that the semicircular contribution actually picks out exactly this operator A. And then the horizontal part has a bound on it. The horizontal part turns out being this expression right here, and we know that the real part of f is less than or equal to 1 by this boundedness property. And so just by analyzing this contour, you're going to be able to convince yourself that a is greater than or equal to 0. So to just very briefly summarize the main ingredients, we're studying this 4-point function, and we realize that in the Light-Cone limit, we get this operator a. And then we're going to use causality and boundedness to convince ourselves that a is actually greater than or equal to 0 using a smart contour integral. So this is sort of the skeletal structure of the ANEC proof. And as we'll see, the QNEC proof is actually going to be very, very similar. But are there any questions at this point about this one?
So what's the psi?
Oh, psi is just a scalar. But I'm just writing it as like, it's acting on the vacuum. It's just thinking about it as some state. So.
But it may depend on coordinates, right?
Yeah. So I'm brushing some of the details under the rug, but strictly speaking, psi is a scalar operator that's inserted at an imaginary time, t equals I delta, say, and so it creates a state at t equals 0.
What's happening with the correlator when the real part of f is 1?
And the real part of that is,
Well, I guess a is just 0. Or?
okay, so
You should be able to see when it's saturated.
okay, yeah. So
The statement that this isn't the leading term in that case.
what's the question?
What's going on with the correlator when the real part of f is 1? Is it the classical limit?
Yeah, I guess it's, I don't know. Yeah, I don't have any smarter intuition other than like it's saturated. This is not in the Light-Cone limit. There's really sub-leading corrections to this correlation. But it's a good question. It's not a good answer, but I'm not sure if I have any better to say.
And the boundedness condition, is this related to the optical thing?
Yeah, exactly.
So maybe you made an assumption of having an interacting fixed point. Why not a fleet? Like, what difference would it make?
Yeah, great question. So the difference would be in this, light cone limit. The assumption that I'm making is that the stress tensor and basically I'm making this assumption that the stress tensor is the dominant contribution to this operator body expansion. In a free theory, what would happen is that you would have higher spin operators that are also minimal twist. And so you would need to take those into account. But of course, like, you don't need this machinery. In the free theory, you can actually just kind of brute force calculate and check that the QNAC actually does hold. So you would combine that. In that free case, you have some other tools you can use. But yeah, great question.
I think that also answers mine, because then I think there's the other part has to contribute to one. Because then it would mean that the leading contribution is zero, which should invalidate the assumption. So in interacting theory, the assumption is
I have to think about that. Yeah, go ahead. Yeah, not 100%. Okay, great. So, any other questions about that? Okay, awesome. So, so how does the QNAC proof work? So actually, I'm going to start with the QNAC summary first because it looks almost exactly like the annex summary. We're gonna I'm defining Q in this way, just to remind you. And what we're trying to prove is that Q is greater than equal to 0. And the proof is going to be structured schematically very much like the annex proof. So we're going to be starting with now some new 4-point function, which I'm going to call capital F, to distinguish it from little f we had before. It's going to be a function of u and v as before, but now also some new parameter, which I'm going to call s. And we're going to study this 4-point function in a very similar way. First, we're going to look at it in a light cone limit. And actually, it turns out a large S limit. In that limit, this function f is going to have the following expansion. So in particular, we see the presence of this operator q. And then we're going to go back and ask these same questions about causality and boundedness and use a contour integral again to pick out the fact that q must have been greater than or equal to 0.
Quick question. Sorry. This expression seems awfully similar to the chaos bound kind of.
Yeah, exactly. So exactly. The ideas we're using here, and so this is so this is the chaos bound paper. Is exactly analogous to. It's just sort of the sorts of ideas that you see. Okay, so what is the 4-point function we're going to study now in the case of the QNAC? Well, here it is. It looks very similar to the ANAC 4-point function in the following sense. We have psi, O, psi, just like we had before. But now we have these sort of funny additional things appearing in the correlation function. E to the I, KAS, e to the minus I, KAS, something involving KD. So let me just tell you the terminology first, and then go through what the actual definitions are. So K, A, and B are something called the full modular Hamiltonian. And this operation of evolving with this operator is something called modular flow. And the parameter S appearing here is sort of like time, but it's called modular time because we're flowing with some other type of Hamiltonian. So what we have is something similar to the 4-point function of the ANAC, but now with modular flow.
sorry.
Yeah.
Why OA bar?
Okay, so those are just grids. So these are labels for coordinates, and I'll explain what they are. Yeah, but they're just scalar operators. Great. So what is a modular Hamiltonian? So this is something that's coming from entanglement entropy. So imagine we have this setup again where we have a Cauchy slice. We have some entangling cut that divides the Cauchy slice into two regions. The Hilbert space of the full space is a product space between the Hilbert space of A and A bar. We can define a reduced density matrix in the usual way by tracing out the degrees of freedom of A bar. Then this quantity here, something is called modular Hamiltonian. It's just defined to be minus the log of the reduced density matrix. And the K's appearing here are something called the full modular Hamiltonian, which is just H of A minus H of A bar. So this is a technical definition, mostly for people who are familiar with these definitions. But probably the main thing to keep in mind though is, okay, what does it mean? Like, what does this evolution mean in terms of modular Hamiltonians? What does modular flow mean? Because that's what's happening here. We're taking this operator and flowing with respect to this modular Hamiltonian. And the answer is actually that we don't know what this modular Hamiltonian does in general. It's in general an extremely complicated and non-local evolution. So at first glance, it seems like a horrible idea. You're taking something you know nothing about and putting it into a correlation function and asking, okay, like trying to prove stuff. But the punchline, so the main thing that we realized is that in the light cone limit, we actually do know what modular evolution does. And the statement is that in the light cone limit, modular evolution just acts like a Lorentz boost, plus corrections that can actually compute. That's very important. We know what these computable corrections are. So in general, modular evolution is something very complicated, something that people are very interested in learning more about and trying to study. And I think our sort of contribution to the story is that, hey, in the light cone limit, this thing is actually very, very nice. And
sorry.
oh yeah.
So this modular Hamiltonian, is it like totally theory independent? Because has it anything to do with the Hamiltonian of the actual CFT?
Okay. So not necessarily. I mean, it's so what's going into it. Well, it depends on the region, how you're dividing. It depends on your entanglement cut. It also depends on the state that you are considering. So it's much more. It's a complicated object. I mean, it has much more ingredients than just the theory. The underlying theory is important, but also the state and the entangling cut are also. That helps. The last point, I just wanted to make was that what we're looking at is double flow. So not just one operator being flowed, but two operators being flowed. And I need to tell you how these two regions are related. So A, again, I'm imagining to be the t=0 slice, which is sort of going in and out of the board. We have some entangling cut and that divides this into A and A bar. The entangling cut for B is just the entangling cut for A shifted in the null direction. So shifted slightly in the null direction. So here, the entangling cut would be sort of going through here, and then this is B, and then this side would be B bar. And B and A bar are just the locations of the two operators. And strictly speaking, what I want is that OB to be located in the domain of dependence of B, and OA bar to be located in the domain of dependence of A bar. That's just labeling sort of where they are on the space-time diagram.
I want to intuitively understand why do you take OA bar instead of OA or anything?
Right. So that's actually the next point. Great question. So just coming back to the summary slide to orient ourselves. I kind of told you a little bit about what these ingredients are appearing in this new 4-point function. The boundedness property is going to be very similar. Just this idea that we're computing an inner product, and this can be bounded by Cauchy-Schwarz. So let's jump right to causality. And causality now is going to be slightly different than the way we use causality in the proof of the ANAC. So in the ANAC, we were using causality in just regular time. But what we're going to use now is causality in modular time. So in this parameter S. And so here, this is the point in the proof where we are going to borrow heavily from results in algebraic quantum field theory. And this is work by Tomita, Takasaki, Borgers, and many others. But very roughly, the conceptual idea is that modular evolution doesn't mess up microcausality. And what do I mean by that? What I mean by that is if I start with two operators that commute, this is the reason for choosing B and A bar. These are operators that initially commute without modular flow having been performed yet. The idea is that once I perform modular flow, the commutation still continues to hold for real S.
Is there a two-way implication? Like, can you go from this side to that side as well?
Sure, I guess you could just set like S equals 0, I guess.
Right.
Let's see. Yeah. I guess so. Great, and so good. So you know that real S is good, but of course, what you expect is that this function, this correlation function as a function of S is actually going to be analytic on some bigger domain, and that's true. And these are things that these mathematicians worked out. And the punchline is that f of S is analytic actually in a strip where the imaginary part of S is goes from minus pi to pi. So this is analogous to kind of like the ANAC statement we had where f of sigma was analytic in the lower half plane. This is the analog of that we need for our QNet. Okay. Yeah.
So, if I understood correctly, the psi states you're inserting at origin.
So these psi states are being, no, so these psi states are being inserted at slightly imaginary time.
In the Euclidean direction. Euclidean time.
We should let him talk first.
Well, yeah, no, it's just setting t equal to I delta, for example. Setting, and what that's doing is creating a state for you at t equals 0. Yeah, that's all it is. Okay, so let me just say a few words quickly about the light cone limit and how one actually evaluates this correlation function to get Q to pop out. Okay, so we want to do something similar. We want to do an operator product expansion of these two operators, O. But of course, it's more subtle now because there's this modular Hamiltonian sitting in the middle. This is just, imagine expanding out this exponential, you're going to end up with stuff like this. And the question is, how do you evaluate this? You can't do a usual operator product expansion anymore. And so the idea is a little bit familiar to people who've worked in entanglement before. It's just something called the replica trick. And this is just the idea that this K, as you remember, if you remember, was just defined as essentially the logarithm of the reduced density matrix. Working with logs is hard, so you just rewrite the log in the following way as some limit of taking the reduced density matrix and raising it to some power. And what that corresponds to in terms of computing in this correlation function is just that you're working in an n-replicated space, in an orbifold theory that has a twist operator. So the whole game now is to learn how to do operator product expansion in the presence of a twist operator. So in particular, this sigma sub n is the twist defect. This could be like O, and you're asking what is the operator product extension of O and O if there's a twist operator sitting in them. And so it should look very much like a usual operator product expansion, but you need to know now what operators can actually appear in this expansion. So what is the defect spectrum? And the punchline is that you end up with the operators that you normally would have expected, the stress tensor and its derivatives, just like you would have gotten in the case of the ANAC. But you actually get a new operator appearing, and this is sort of a very I would say one of the really interesting things about this calculation is that you see a new operator appearing. It appears at order n minus 1. At the end of the day, we're going to take the limit n equals 1. So you would think maybe this guy would disappear, but it actually has a non-zero contribution in the n equal to 1 limit. And so this operator is called the displacement operator. And the displacement operator, its presence in this OPE is actually what's going to give us S double prime. And to make a long story short, the punchline is just that the expectation value of this displacement operator is related to differentiating the entanglement entropy. And so if you imagine like you're doing this operator product expansion, you have T is appearing, that's great, that's essentially going to give us this at the end of the day. And then you have this extra term, this displacement operator, that's what's going to give us S double prime sitting here. So I've said a few words kind of about the skeletal structure of this proof. And again, this was not meant to be a detailed, fully detailed description of everything involved, but just to sort of lay out what are sort of the main ingredients. Because I think the ingredients that go into this, they're the same ingredients that go into the Anak proof. They're very similar ingredients that go into the proof of the chaos bound. And so there's this string of ideas of using correlation functions, taking causality, and trying to tease out information about QFT from studying correlation functions and causality that I think is extremely important. And there's, I think we haven't fully learned yet everything that we can learn using these sorts of methods. Great, so what's the overall summary? The overall summary is just to remind you again what the QNet is. It provides a lower bound on the stress tensor in QFT. It's a striking relation between energy and entanglement, and it's now a proven statement in QFT. And some of the crucial ingredients in new technology that went into the proof included this idea of modular flow, something you can define, but conceptually, what is it doing actually? These are very interesting questions. The light code limit, operator product expansion in the presence of a defect operator. And just to sort of close with something on the horizon, once you have an inequality, an extremely interesting question, of course, to ask is when is this inequality saturated? When does this null component of T actually equal S double prime? And one of the things we've learned in the last year is that it's actually true in the holographic CFTs. This equality holds when you have a simple half-space entanglement cut. And in particular, it may be true more generally in QFT as well. So stay tuned for I think results I think will be upcoming about these sorts about saturation of the QNet. Thank you very much.